Hey there, Saber Power people. Welcome to this week's edition of Think. We are experiencing technical difficulty. Please stand by. Well, here's what I sent last week. It's just a simple differential circuit wrapped around a transformer. So what we have to do is break down the CT ratios, the transformer ratio, and determine which way the current is flowing through the circuit. So let's look at question 1. What is the amount of current flowing in the secondary side of the 200 to 5 CT current circuit? That's this guy right here. So first we're going to have to take the CT ratio 200 to 5 and turn it into a ratio to 1. How do we do that? CT ratios aren't that tough, but it does take a little bit of math. Just for fun, I picked a 600 to 5 CT, and we want to bring that to a ratio to 1. How do we do it? Well, we can go back to grade school and do it the long division way, and that's okay. How many times does 5 go into 6? One time. Multiply 5 by the 1, and then subtract the 5 from the 6, and you're left with 100. How many times does 5 go into 10? 5 goes into 10 two times, and you multiply the 5 by the 2, subtract the 10 from the 10, and you're left with 0. Bring the 0 up, and you have the number 120 to 1. So a 600 to 5 CT is the same as 120 to 1. Guys a whole lot smarter than me can just do it in their head. 600 divided by 5. 5 goes into 6 one time, and 5 goes into 120 times, and so your number is 120 to 1. I can't quite do it that fast, but I learned something several years ago. I was in a class with a bunch of technicians, and there were some young engineers there, and we were talking about CT ratios and how to come about the ratio to 1. Well, this one young engineer raised his hand and said, hey, I've got a little trick I use if you're interested. And all of us seasoned technicians sitting around the table were saying, yeah, sure, rookie, show us what's up. And so he said, you know, what I do is I take off the last 0 and then multiply the number by 2. And so you take off the last 0, and then you multiply 60 by 2, and you come up with 120 to 1. Well, all the seasoned technicians kind of laughed at the guy and thought the guy was silly. And this is something I've taken with me for many, many years. And by the way, you know what they call that silly young engineer now? Boss. So let's try a couple. 1200 to 5 CT. Take off the last 0. Multiply 120 by 2. Simple, right? 240 to 1. How about this? 2000 to 5. Take off the last 0. Multiply by 2. 400. I like this method. 800 to 5. Take off the last 0. Multiply by 2. That's right. 160 to 1. One more. 200 to 5. Oh, that happens to be the one we're dealing with right now. 200 to 5. Take off the last 0. Multiply by 2, and you get 40 to 1. So what is the amount of the current flowing in the secondary side of the 200 to 5 CT at point number 1? 200 to 5, take off the last 0, multiply by 2, 40 to 1. 1 amp flowing in the secondary circuit. All right, moving on to number 2. Which arrow at point number 2 indicates the direction of the current flow? Is it the top arrow or the bottom arrow? So now we're going to have some fun. I looked on the internet to find a picture that might help me explain current flow, and this is the best one I could come up with. It shows the primary current flowing through the hollow core of the CT, and if you look close, you can find the secondary one. Anyway, this just didn't do it for me. It got a little busy, a little fuzzy for me, so I needed to make it more simple for me to understand. So I drew this one line diagram of one CT and one circuit. So here's the explanation. for any current transformer. All right, for any current transformer, the current flowing out of the secondary directly corresponds to the current flowing into the primary. So, where it flows in, it flows out. All right, get that. Where the primary current flows into a CT, at that point on the secondary side of the CT, the secondary current is flowing out. All right, you notice that on this diagram that there are no polarity marks because the polarity marks do not change the electrical circuit at all. It doesn't change the electrical properties of this circuit at all. So you could put them on there, and the same holds true. If the current is flowing into the polarity in the primary, it flows out of the secondary at polarity. And on CTs, we call polarity on the primary side H1, and on the secondary side, we call polarity X1. But you could move the polarities down this way. You could roll the CT over, swap it. And if the primary current flows into the non-polarity, then the secondary current will flow out of the non-polarity. So the polarity marks don't change the electrical properties at all. The polarity marks are just there to show you how the CT is positioned inside the piece of equipment. So here's a differential circuit. Notice that primary current is flowing into the top of the CT. Therefore, the secondary current is also going to flow out of the top. Same on both sets of CTs. So let's start playing with it just a little bit. We'll add some polarity marks in here. So now I have polarity marks on the top and polarity marks on the bottom, and you see that it doesn't affect the current flow whatsoever. I could even change the polarity marks like this, swap them around, and it still doesn't change the current flow. We could do it like this, with the top set of CTs pointing away and the bottom set of CTs pointing in, and it still doesn't affect the current flow. What it does tell us is the position of the CT inside the piece of equipment, so we know how to wire the protection circuit. We are either going to make our phase wires connect to polarity or non-polarity, and that's the importance of checking out these CTs. So the polarity on the top one is pointed away from the equipment, and the polarity on the bottom one now is pointed toward the equipment. And so we know that on the top set of CTs, we'll wire to polarity, and on the bottom set of CTs, we'll wire to non-polarity. So which arrow at point number 2 indicates the direction of the current flow? Top arrow or bottom arrow? Top arrow. So how much current is flowing on the secondary side of the transformer? Well, we have 40 amps on the primary. How many amps do we have on the secondary? So let's look at turns ratio. Well, N represents the number of turns. V represents the voltage, and I represents current. So if there are 10 turns to every 1 on the transformer, meaning that there are 10 turns on the primary, there's 1 turn on the secondary, then when you apply voltage to it, for every volt on the primary, for every 10 volts on the primary, there'll be 1 volt on the secondary, okay? 10 volts on the primary, 1 volt on the secondary. Now the inverse is true for current. For every 1 amp on the primary, there will be 10 amps on the secondary. So what does that mean for us? So we have a transformer that is 138 kV to 13.8. So if you divide the 13.8 into the 138, you get a 10 to 1 turns ratio. So now we take the 40. So for every 40 amps on the primary, how much current do you have on the secondary? You have 400. All right, so 400 amps. On to number 4. To match the current flow which is being produced by the 200 to 5 CT on the primary side of the transformer, what does the ratio need to be for the CT on the secondary side of the transformer? Well, the primary side CT, it has 1 amp on the secondary. So we need to have 1 amp on the secondary of the bottom CT. So we know 400 amps is flowing through that CT. So we know we need 1 amp on the secondary. We have 400 on the primary side and 1 amp on the secondary side. What would that be to a ratio of 5? Well, multiply 400 by 5 and you get 2,000 to 5. Now for number 5, how much current is actually flowing through the relay? It's just fun stuff here. So we know that the top CT has 1 amp in the secondary with a current flowing in that direction. We also know that the bottom set of CTs has 1 amp flowing out of it in that direction. So if 1 amp is leaving the CT, 1 amp must go back to the CT. That makes sense, right? So if 1 amp is being sent, 1 amp has to return to the CT. Just like this. So now the current travels in this direction, and when it reaches this point, something needs to happen. It's a branch circuit, so some is either going to go through the relay and some go back to the CT, but how much? Well, the CTs are saying, I need 1 amp to return. And so the amp continues on in that path, and then 0 amps flows through the relay itself. And we're almost done. What's the IEEE device number for this relay? Well, we've been talking about it. This is a differential circuit. So a current differential circuit is identified by the IEEE number 87. This differential is wrapped around a transformer, and a transformer is represented by a T. We also know that there are other types of differentials like bus differentials, motor differentials, line differentials, but in this case, it's a transformer differential. So for our relay, it's an 87T. Well, there you have it. Another thing to think about, thought out. I hope you had fun with it. We work on protective equipment and devices for electrical power systems. We work on old stuff like electromechanical relays, and we work on the newest state-of-the-art microprocessing devices. But at the end of the day, just electricity. And electricity hasn't changed. What is changing, though, is the way we monitor and protect electrical systems. Our devices are getting smarter. Now, one relay can replace an entire panel of relays. Now, we also have software that will actually run our test equipment for us and give the equipment a grade. We got to remember, though, that that software is just a tool, and we as technicians must know what the expected test results are going to be before we even push that button. I'm looking forward to getting together with you and digging deeper down into these details. But until then, stay sharp, be strategic, and do every task with surgical precision. Oh, and by the way, Merry Christmas.